Take one. Please state your name, role, and project.
Hi, my name is Ritik Makhija. I'm the team lead for Team 24/18, and our project is to understanding the normal aging brain so that the puzzle of Alzheimer's can be solved. This video documents our progress over the project and highlights what we've accomplished so far and what we plan on accomplishing with this project.
I'm Gunta Shara and I'm the procurement lead.
I'm Max Duque and I'm the mechanical lead.
I'm Jason Freeman and I'm the electrical lead.
I'm David Polk and I'm the software lead.
This is the Evelyn F. McKnight Brain Institute. Located in the heart of the medical campus of University of Arizona, this institute is responsible for studying brain behavior as well as conducting research on Alzheimer's disease. There are currently 40 million people worldwide suffering from Alzheimer's disease. That's roughly 1 in 9 people over the age of 65. Brain degradation and memory loss are two of the main symptoms of Alzheimer's disease, where eventually it leads to a stage where the patient is even unable to perform basic tasks. And the worst part is, the main reason behind this disease is yet unknown, so therefore new research has to be conducted to help solve this puzzle. To tackle this issue, the researchers at the Evelyn F. McKnight Brain Institute are conducting behavioral studies on young and old rats. This study is applicable because the rats share a similar functionality as well as structure of the brain as compared to humans. These tests are performed here in the ICR arena.
This is the instantaneous cue rotation or ICR arena. During the circular track trial, a gradient is projected on the walls of the ICR arena and a trained rat stops at specific cue points. At these points, the rat is fed using a food reward and ethanol dispensing robot, or FRED for short. This system tracks the rat using positional data, and depending upon its performance, it is fed a variable amount of liquid food. The robot also cleans up after the rat droppings during the trial. So the original robot no longer syncs with the ICR, causing the system to be non-operational. On top of that, the overall design of the robot is congested and it is equipped with out-of-date electronics, making it almost impossible to work on. Another major issue is that the wireless brainwave reading system is too heavy, affecting the rat's natural movement, ultimately skewing the data.
With these issues in mind, we were asked to redevelop the system with improved functionality. Our first goal was to make this robot more modular, lighter, as well as update the electronics. Our second goal was to build a frictionless tether system that allowed for wired brain data communication without indicating any positional cues to the rat.
Now let's break down the FRED robot design. The FRED robot is comprised by 3 main subassemblies. Firstly, we have the feeding subsystem, which is comprised by a feeding arm that allows the food to travel from the reservoirs to the feeding plate where the rat will eat from. When the steel wire is pulled, the feeding plate will extend. From there, a pump will then dispense food onto the feeding plate. The casing also contains a tube connected to the reservoir filled with liquid food. This food is used to reward the rat during the circular track trials. The second subassembly is a cleaning mechanism. This is in charge of collecting all of the rat's droppings throughout the trial. Lastly, we have the electrical subassembly. This handles all of the data processing and actions performed by the robot. This includes an SD card that logs all actions for debugging and system verification. An XP module that handles wireless communication to and from the robot. Motors and motor drivers to control the robot's movement. And of course, an Arduino microcontroller. The robot also contains many other auxiliary components, such as a custom PCB board used for wiring all of our components together. Also, a proximity sensor for rat safety, and an LCD screen along with buttons for manual use.
Let's talk about the mechanical design of the FRED robot. The chassis and wheels needed to be less than 4 inches wide to fit in the narrow track of the ICR, while housing all the electrical components. This led to a falsely curved design of the robot with 3 different sections. The robot also has rear-wheel drive with a rear driving motor and is supported by a front wheel and a guide arm. The chassis has an extrusion on the side facing the inside of the arena, which serves a dual purpose, a shelf for the battery and a connection to the guide arm. The guide arm was custom designed to roll with little friction along a guide rail pre-built along the inside of the circular track. This guide arm also supports the feeding mechanism. The casing was designed to house the steel wire and feed tube separately and curved to follow the track. The length was designated so that there would be no electrical interference between the brainwave reading system and the robot.
The code base for this project is divided into 3 different languages. Firstly, we have the Arduino code, which is written in C++. The codebase for the original robot was written in 12,000 lines, all contained in one single file. For our codebase, we reduced this down to 1,500 lines, separated into 7 different files depending on the robot's functionality. Minimal edits were made to the other 2 codebases. The first of which includes the MATLAB GUI, which allows a researcher to set parameters before and during tests, and also allows them to monitor progress throughout these tests. The last codebase we worked with was the C#, which essentially acts as a backend to the rest of our system.
To further elaborate on the startup, the C#, MATLAB, the Neuralinks module, Cheetah, and the robot all need to run on a synchronous clock. This is achieved using wireless packet sending between these systems. This synchronized clock is used to log the rat's brain readings with accurate positional data. The camera was originally positioned above the ICR arena, but with the introduction of the tether system, the camera had to be moved to fit within the arena. The new position of the camera is placed further down within the system. This change allows the tether system to move properly while minimizing obstruction to the camera feed.
As mentioned before, the purpose of the tether system is to keep the data transmission tether normal above the rat's head and not interfere during the experiment or give the rat any positional indication. The tether that transmits the brain data is connected to a commutator that is mounted 2 feet above the ceiling of the ICR. This commutator is an active system that untangles the tether as the rat traverses through the trial so that the tether does not get damaged.
Our final testing involved the implementation and integration of old design systems in the ICR arena. These tests congregate into 2 final tests for the system, the ICR Open Arena Trial and the ICR Circular Track Trial test. The ICR Open Arena Trial test utilizes the entire tether system running together as a rat moves around the entire open arena of the ICR. The ICR Circular Track Trial test utilizes both the robot and tether systems in their entirety, as a robot follows around the RC rat that is attached to the tether system in a fully simulated ICR trial.
We truly believe that our project will play a crucial role in understanding the puzzle of Alzheimer's disease. To further increase the functionality of this system, a small rat elevator could be constructed that would help in placing the rat inside the ICR arena while the tether remains connected to it. We, as a team, are willing to bet all this money that our project will play a crucial role in the fight against Alzheimer's disease.